Using simple factorization to plot quadratic graphs. In Chapter 6 and Chapter 9, we explained that quadratic equations with one variable, we have the following shown on screen, can be solved by factorizing the left part to show it as a product of two expressions in the brackets. This can only be done in two cases out of three possible scenarios. Case 1, when the quadratic equation has two distinct roots, i.e. when the discriminant delta is positive. In this case, the equation is written in the form, we have the following shown on screen. We have the following shown on screen. When the task is to plot the graph of a quadratic equation with two variables, we have the following shown on screen. We ignore the existence of variable y first and try to factorize the part containing variable x according to the above rules. The factorization allows us to find the x-intercepts, as each solution corresponds to an x-intercept. We write the factorized form of a quadratic equation with two variables, we have the following shown on screen. And when solving it, we take y equals 0, we have the following shown on screen. Where x1 and x squared are the solutions, roots, of the quadratic equation with one variable, which correspond to the x-intercepts of the same quadratic equation but with two variables when shown in a graph. The rest of the points are identified in the same way as when using the quadratic formula to find the roots, exactly as we did in the previous tutorial. Let's see an example to clarify this point. Example 1. Plot the graph of the following quadratic equation using the factorizing method. We have the following shown on screen. Solution 1. We have a equals 2, b equals 7 and c equals 3. Given the relations, we have the following shown on screen. 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 Thus, combining the equations yields p equals 1, q equals 2, m equals -3 and n equals -1. Therefore, the factorized equation, we have the following shown on screen. We have the following shown on screen. Therefore, at the points where the x-intercepts are, we have x, a -3, equals 0, so x, a equals -3, or 2, x, b plus 1, equals 0, so x, b equals -1 over 2. The corresponding y values, we expect them to be both 0, we have the following shown on screen. We have the following shown on screen. The two x-intercepts therefore are a, -3, 0, and b, -1 over 2, 0. As we said in theory, the rest of the solution is the same as in previous examples. Thus, the x-coordinate of the vertex v, we have the following shown on screen. As for the y-coordinate of the vertex, we substitute the above value in the original equation. Thus, we have the following shown on screen. Thus, we have v, -7 over 4, -25 over 8. The y-intercept, for x equals 0, is y, c equals 3. Therefore, the y-intercept is at c, 0, 3. In the same way as before, we also find the symmetrical point D of the y-intercept. Thus, from the half-line segment formula, where x, v is the midpoint of c, d, x, we have the following shown on screen. Thus, we have d, -7 over 2, 3. Now, let's plot the graph using the 5 points found above, i.e. a, minus 3, 0, b, minus 1 over 2, 0, c, 0, 3, d, minus 7 over 2, 3, and v, minus 7 over 4, minus 25 over 8. We have the following shown on screen. Case 2, when the quadratic equation has a single root, when the discriminant is 0. In that case, the part containing the independent variable can be written as a binomial expression, so the equation is written in the form we have the following shown on screen. Where m is a coefficient and n is a constant. The corresponding quadratic equations with one variable of the type we have the following shown on screen. Have a single solution, root, of the form we have the following shown on screen. Let's see what is the relationship between the original coefficients and constant a, b, and c with the new ones, m and n. Thus, since the original form of the quadratic equation with two variables, we have the following shown on screen. And given that we can express the new factorized form, we have the following shown on screen. Then we have the following shown on screen. In this way, we can find the coefficient m and the constant n if we are convinced that the original quadratic equation has a single root. Why do we need all this? Well, having a single solution means having a single contact point with the x-axis, which corresponds to the vertex v. Look at the figure, where the graph of the quadratic equation y equals x squared minus 4x plus 4 is shown. It does not take much to prove that this quadratic equation's factorized form is y equals x minus 2 squared. We have the following shown on screen. The only solution of the corresponding quadratic equation with one variable x squared minus 4x plus 4 is equal to 0 is x equals 2, which corresponds both to the x-intercept and the vertex v. The question that arises here is, where to find the other points needed for the graph? Well, like in other cases discussed earlier in the previous tutorial when there were no x-intercepts, or when the quadratic graph had a single x-intercept, after finding the vertex you can choose 2 points on both sides of the vertex that have the same horizontal distance from it and find their y-coordinates. These points have the same effect as the x-intercepts when the parabola intercepts the graph in two different positions. Likewise, we can still use the y-intercept and its symmetrical point concerning the vertical line drawn from the vertex, as we have done in all the other cases discussed in the previous tutorial. Example 2. Plot the graph of the quadratic equation. We have the following shown on screen. Using the factorization method. Solution 2. We have the following shown on screen. Therefore, the only point where the graph intercepts the x-axis, we have the following shown on screen, which corresponds to the vertex v, 1, 0. Let's find the y-intercept now. Thus, for x equals 0, we have y equals 4. Therefore, point C, 0, 4, is the y-intercept. The symmetrical point to C is point D with coordinates D, 2, 4. This is because the vertex is at x equals 1, and given the formula of segment midpoint, we have the following shown on screen. We obtain after substituting the known values, we have the following shown on screen. It is also known from previous examples that point D has the same y-coordinates as point C. Hence, we have D, 2, 4. We can also find 2 points A and B equidistant from the vertex in the horizontal direction on both of its sides. For example, since x, v equals 1, we can choose x, a equals -1 and x, b equals 3. The corresponding y values, we have the following shown on screen. We have the following shown on screen. Therefore, we have a -1, 16, and b 3, 16. Next, we insert all the 5 points found, a -1, 16, b 3, 16, c 0, 4, d 2, 4, and v 1, 0, in the coordinate system and plot the graph by connecting them smoothly. We have the following shown on screen. Case 3. When the discriminant is negative, there are no x-intercepts at all, so it is impossible to factorize the expression containing the independent variable. Therefore, we use the same procedure as above to find the necessary points to sketch the graph. Thus, first, we find the vertex v, then the point C that corresponds to the y-intercept, then its symmetrical point D, and at the end, two equidistant points from the vertex, one on its left and the other on its right side. Then, we plot the graph based on these 5 points. Example 3. Plot the graph of the quadratic equation. We have the following shown on screen. Solution 3. We have a equals -1, b equals 3, and c equals -4. The discriminant delta, we have the following shown on screen. Since the discriminant is negative, the parabola has no x-intercepts. It has a maximum at the vertex v, which is below the x-axis. First, we find where the vertex v is situated. Its x-coordinate, we have the following shown on screen. Since the discriminant is negative, we cannot use the standard formula of the y-coordinate of the vertex, but simply substitute the x-coordinate of the vertex in the main equation. We have the following shown on screen. Hence, we have v 3/2 minus 7/4. Next, let's find the y-intercept c. We already know that xc equals 0, so substituting this value in the main equation yields yc equals -4. Therefore, we have c 0, -4. Using the segment midpoint formula, we can also find the symmetrical point to c, which we denote by d as usual. We have the following shown on screen. We know that the y-coordinate of point D is the same as that of C, so we have D, 3, -4. Now, let's find two other symmetrical points A and B on either side of the vertex to complete the set of the necessary points to plot the graph. Since the x-coordinate of the vertex is a fraction, for simplicity we add and subtract it with another fraction, say 5/2, to obtain whole numbers. Therefore, we have the following shown on screen. We have the following shown on screen. For the corresponding y values, we have the following shown on screen. We have the following shown on screen. As expected. Therefore, the last 2 points are A, -1, -8, and B, 4, -8. Hence, inserting in the coordinate system all the 5 points found, A, -1, -8, B, 4, -8, C, 0, -4, D, 3, -4, and V, 3/2, -7/4, yields the following graph. After connecting the points smoothly, we have the following shown on screen. That is all for lesson 15.2.1. To continue this tutorial, please watch 15.2.2, using the completing the square method to plot quadratic graphs. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.